we want to look at the relationship between electric field and electrostatic potential. We've already looked at the relationship between force and potential, and we just want to abstract that to the electric field a little bit. So if we have a charge Q and a test charge Q sub t, the test charge Q sub t at x equals a, Q at x equals 0, if we want to move along the x-axis a distance delta r, and in this case this looks like we're moving closer to the charge, so we're doing an a minus delta r. We're going to push this charge in closer to Q. Now if Q is a positive charge, we have to do work in order to do that. If Q is a negative charge, then a positive test charge here could be harnessed to a generator or something as we move from here to here. It could actually perform useful work, so that in the first case where we have a positive charge here, we have to do positive work to move the charge closer. And in that case we would say that the field itself is doing negative work on the charge. On the other hand, if this is a negative charge, then the field is actually pulling the charge in, and the field is doing positive work. We are doing negative work on the charge in our attempt, in our restraining it and keeping it from going any further. So, how does all this relate to the electric field? Well, the electric field at point A we'll call E sub A kq over a squared. Little a squared, of course, is the square of the distance, because at this point our distance is little a. Then the force exerted on the test charge is, of course, going to be the test charge times the electric field, which is going to be this, the same expression that we get from Coulomb's law. That's just the electric field at A times the charge qt. So again, to get the force, we could use Coulomb's law, or we could just say electric field times q sub t. Now this obviously has something to do with the work that we have to do. We're going to have to exert a force equal and opposite to the force exerted by the field. And in order to move the charge from here to here, then, we're going to have to do work, delta W, which is negative Fa times delta R. Okay, our work here is going to be the result of a force equal and opposite to the electric field force at the point. The electric field force is F sub A, again obtained from the electric field times the charge. And then we multiply that by the distance delta r that we move the charge. We see that the work that we do over distance delta r over displacement delta r is negative Ea times qt delta r. That's because Ea times qt is just your Fa. So that the change in electrostatic potential, which is just the work over the test charge q sub t, is going to be the work negative Ea qt delta r divided by the qt, and the qt divides out. It just gives us negative Ea delta r, assuming a small delta r. Now this approximation is good to the extent delta r is small. Between 2 points A and B, if we have the charge Q here, we have a point A, a point B. If we move the charge from point A to point B, we have lots and lots of little delta r's. If we divide this interval into more and more little delta r's, we get more and more accurate approximations of how much work we get from A to B. We get these approximations by adding up the contributions to the voltage. Okay, the change in voltage between A and B is the sum of the negative E delta R contributions. Remember that what we got down here was E delta R, essentially negative E delta R, gave us the work required to move from here to here, where the electric field is evaluated at this point, of course. Now, we'll do a little calculus for a minute, but everybody should understand that we just sum up all the negative E delta R contributions from A to B to get the change in potential between A and B. Okay, now we do the calculus. We write this as an integral. Okay, we take the limit of the sum as the delta R's go to 0, and we get the integral from A to B of negative E of r dr. E of r, of course, is just the electric field of the charge q, which is just kq over r squared. So we have the integral from a to b of negative kq over r squared dr. And that integral is easily calculated, and we get k times q over b minus q over a. Now recalling that kq over b is just the kq over r at x equals, or r equals b, and this is the kq over r at r equals a, we see that we just have the potential at b minus the potential at a. But in this case, we've derived it from the electric field, not from the force vectors, as we did before.